For a moment, you simply notice the room around you. Perhaps there is a soft warmth in the air, the gentle comfort of a blanket, the quiet rhythm of your breathing moving slowly in and out. Warmth and coolness are such familiar feelings that most of the time you hardly notice them. Yet these sensations are small reminders of something much larger, something that exists everywhere in the universe. Temperature. It is one of the quiet languages of nature. Your body feels it constantly. The warmth of sunlight on your skin, the cool touch of evening air, the comforting heat of a cup of tea resting in your hands. These simple experiences are not just feelings. They are tiny messages from the invisible world of atoms and molecules, endlessly moving around you. Because temperature, in its simplest form, is motion. Imagine for a moment that everything around you is made of tiny dancers. So small that no eye can ever see them. These dancers are atoms, the basic building blocks of matter. They vibrate, spin, bump into each other, and glide through space in an endless microscopic dance. When they move quickly, we call that warmth. When they move slowly, we call that cold. Even the air you breathe is full of these dancers. Each breath carries trillions upon trillions of molecules drifting through space, colliding gently, transferring energy like whispers passed from one traveler to another. But here in your room, these dancers are lively. Not chaotic, but energetic. They move with enough motion to create the comfortable warmth you feel around you. Now imagine slowly drifting outward. Your mind moves gently beyond the walls of the room, beyond the roof above you, rising quietly into the night sky. Below you, the earth turns slowly, wrapped in a thin blue atmosphere that holds warmth close to the surface. This delicate blanket of air traps heat from the sun, creating oceans, winds, clouds, and the countless living systems that make our planet feel alive. But as you rise higher, something begins to change. The air grows thinner. The warmth fades. Up here, the dancers move a little slower. By the time you reach the edge of Earth's atmosphere, the environment has become something very different from the world below. Space begins here, not with a dramatic line, but with a gradual fading of air and warmth. And space is quiet. Not silent in the way an empty room is silent, but vast and open. There is almost nothing here to hold warmth in place. Heat, which on Earth moves easily through air and water, finds far fewer pathways in space. Without air to carry warmth, temperature begins to behave differently. You drift farther outward. The earth below becomes a small blue sphere, glowing softly in sunlight. The sun itself shines bright and steady, pouring enormous energy across the solar system. Wherever its light touches a surface, warmth appears. But wherever its light cannot reach, cold quietly gathers. Temperature in space is not evenly spread. Instead, it is a patchwork of warmth and cold, shaped by sunlight and shadow. A satellite floating in orbit may have one side warmed by direct sunlight, while the opposite side sits in deep shadow, becoming incredibly cold. Astronauts working outside their spacecraft carefully manage this balance, because even small shifts between light and darkness can change temperature dramatically. But beyond Earth's orbit, the sunlight begins to weaken. Each step farther from the sun spreads its energy thinner and thinner across space. Mars receives less warmth than Earth. Jupiter receives far less still. And beyond the giant planets, the sunlight becomes little more than a faint glow. Out there, in the distant reaches of our solar system, temperatures fall far below anything most people experience on Earth. Frozen worlds drift through darkness, their surfaces locked in deep cosmic winter. Yet even there, the dancers continue their motion. Even the coldest ice still contains atoms gently vibrating in place. This is one of the most comforting truths in physics: motion never truly disappears. It only slows. You continue drifting outward, leaving the solar system behind. Now the sun becomes just another star among billions. Its warmth fades into the vast ocean of interstellar space, where distances between stars stretch across unimaginable scales. Here, the temperature drops even further. The gas drifting between stars is incredibly thin, far thinner than any vacuum we can create on Earth. With so few particles present, collisions become rare. Energy spreads out slowly, and motion becomes gentle and quiet. The dancers are still moving, but their dance is slow now, almost dreamlike. This immense region between stars holds temperatures only a few degrees above a remarkable point in physics known as absolute zero, the theoretical limit where atomic motion becomes as slow as nature allows. You may imagine this place as deeply cold, and it is. But it is also peaceful. Because cold, in the universe, does not always mean harsh or hostile. Often, it means calm. A slowing of motion. A quieting of energy. A cosmic stillness spreading across the darkness. And yet, something even more surprising waits deeper in space. Because even in the coldest darkness between stars, there is still a faint warmth lingering everywhere. A whisper of energy left over from the earliest moments of the universe itself. A glow so ancient and so gentle that it fills all of space like the softest background hum. Astronomers call it the cosmic microwave background. It is incredibly cold, only about 2.7 degrees above absolute zero. Yet it carries with it the memory of a universe that was once unimaginably hot. Long ago, everything was filled with blazing energy. The entire cosmos was a sea of light and heat. But over billions of years, the universe expanded. And as it expanded, it slowly cooled. Like embers from a great cosmic fire fading across time. As you drift quietly through space, surrounded by this faint ancient warmth, you begin to realize something beautiful. The universe itself has been slowly cooling for billions of years. And that quiet cooling, that gentle fading of motion, is only the beginning of the story. Because to truly understand the coldest places in the cosmos, you must travel even closer to one of physics' most mysterious ideas. A place where motion slows almost completely. A place scientists call absolute zero. Now your journey continues, drifting quietly through the dark ocean of space. Behind you, distant stars glow like scattered lanterns. Around you, the universe feels vast, calm, and deeply still. The faint ancient warmth of space surrounds you like the softest whisper. Yet even here, where temperatures are already incredibly low, something even colder exists, not a place you can easily travel to, but an idea. A boundary. A limit written into the laws of physics themselves. Scientists call this boundary absolute zero. To understand it, you return once more to the tiny dancers of the universe, the atoms and molecules that make up everything you see, touch, and feel. Every object, no matter how solid it appears, is full of motion. a wooden table, a stone mountain, even the quiet air resting in a room. Inside each of these things, atoms vibrate constantly. They jiggle, twist, and move, bumping gently against their neighbors. This motion is usually far too small to notice, but it is always there. And the faster those atoms move, the warmer something becomes. You may imagine them like dancers at a lively gathering. When the music is energetic, the dancers move quickly, spinning, jumping, and shifting across the floor. The room feels warm, full of activity and motion. But if the music slows, the dancers begin to move more gently. Their steps grow smaller. Their rhythm softens. In the language of physics, cooling is simply the slowing of this dance. When temperature drops, atoms lose energy. Their movements become smaller and quieter. Vibrations soften. Collisions become less frequent. The dance continues, but more slowly. Scientists measure temperature using several different scales, but one of the most important for physics is called the Kelvin scale. Unlike the familiar Celsius scale, which places 0 at the freezing point of water, the Kelvin scale begins at the coldest possible temperature. Absolute 0. On this scale, absolute 0 is written as 0 Kelvin. It corresponds to about minus 273.15 degrees Celsius, or minus 459.67 degrees Fahrenheit. These numbers may sound astonishingly cold, and they are. But the meaning behind them is even more fascinating. Absolute 0 represents the point where atomic motion becomes as small as nature allows. The dancers slow almost completely. Their steps become tiny tremors. Their movements shrink until only the faintest possible vibrations remain. For a long time, scientists wondered if reaching this ultimate stillness might actually be possible. Could you remove enough energy from a system that its atoms would finally stop moving altogether? At first, the idea seemed simple. Just keep cooling something. Remove more and more heat. Slow the dancers further and further. But nature holds a subtle rule here. No matter how carefully scientists cool a system, they can never remove every last bit of motion. There is always a small remainder, a faint trembling that cannot disappear completely. This tiny leftover motion comes from one of the deepest principles of the universe, quantum mechanics. At the smallest scales of reality, particles cannot sit perfectly still. The universe itself contains a kind of built-in uncertainty. Even at absolute 0, atoms must retain a tiny flicker of movement. This means that absolute 0 is not a temperature that can truly be reached. It is a limit, a horizon, a place scientists can approach endlessly but never quite touch. You might imagine walking toward the horizon on a long, quiet beach. No matter how far you travel, the horizon remains ahead of you, always just out of reach. Absolute 0 is like that horizon of cold. Scientists have come astonishingly close to it. In laboratories around the world, researchers have cooled atoms to temperatures only billionths of a degree above absolute 0. At these incredible conditions, the dance of atoms becomes so slow that entirely new behaviors begin to appear. Matter starts acting in strange and beautiful ways. Particles that normally behave like separate individuals suddenly begin moving together, almost like a synchronized choir. Their motions merge into a shared rhythm, forming unusual states of matter that seem almost dreamlike. But these experiments come much later in our story. For now, your journey remains in the quiet depths of space, where temperatures are already very low but not quite close to absolute zero. In fact, something surprising fills the entire universe with a gentle warmth that prevents space from ever becoming completely cold. Even the emptiest regions between galaxies contain a faint background glow. This glow is incredibly subtle. It does not come from stars, or planets, or galaxies. Instead, it comes from the earliest moments of the universe itself. More than 13 billion years ago, the cosmos was once unimaginably hot and dense. Everything was compressed into a glowing sea of energy, where particles and light moved in an intense storm of heat. As the universe expanded, that heat slowly spread outward. Energy diluted across larger and larger distances. And over billions of years, the entire cosmos cooled. The blazing fire of the early universe gradually faded, leaving behind a faint afterglow that still fills all of space today. This ancient radiation surrounds you everywhere you travel in the cosmos. It is extremely cold, only about 2.7 Kelvin above absolute zero. Yet it never disappears completely. No matter how far you drift into the darkness between stars, that faint warmth remains. It is like the quiet memory of a long-extinguished fire. Astronomers discovered this cosmic glow in 1965, almost by accident. Two scientists, Arno Penzias and Robert Wilson, were studying radio signals when they noticed a mysterious background noise coming from every direction in the sky. At first they thought it might be interference, perhaps something from their equipment or even pigeons nesting nearby. But after careful investigation, they realized the signal was something extraordinary. It was the leftover heat from the birth of the universe. A whisper from the Big Bang itself. And because this faint radiation fills all of space, it sets a natural temperature floor for the universe. No place in ordinary space can easily become colder than this background glow. Even the most distant, empty regions still contain that ancient warmth. But as you continue drifting through the quiet cosmos, another thought begins to form. You continue drifting quietly through the vastness of space. Around you stretches a darkness so deep it feels almost endless. The stars you saw before are now distant points of light, scattered across a cosmic ocean. Their glow is gentle, patient, and ancient. Yet even here, in what seems like emptiness, something surrounds you. Not darkness alone. There is a faint warmth, almost impossible to notice, filling every corner of the universe. It is subtle beyond imagination, softer than the faintest whisper. And yet it is everywhere. This quiet glow has a story that reaches all the way back to the beginning of time. To understand it, your journey must travel not just across space, but across time itself. Far back, more than 13 billion years ago, the universe was very different from the calm and spacious cosmos you see now. In those earliest moments, everything was hot. Not just warm like sunlight on your skin. Not even hot like molten lava or the center of a star. The universe was so hot that atoms could not even exist yet. Imagine an ocean made entirely of light and energy. Particles collided constantly, moving with incredible speed. Photons, tiny packets of light, bounced endlessly between particles in a glowing storm of motion. There were no stars yet. No galaxies. No planets or nebulae. Only a bright, dense sea of energy expanding outward in every direction. This early universe was filled with light, but it was a chaotic light, trapped inside a thick cosmic fog. Photons could not travel far without crashing into particles again and again. It was like trying to shine a flashlight through a dense cloud of smoke. The light was there, but it could not move freely. As the universe expanded, however, something important began to happen. Expansion stretched space itself, gently spreading everything farther apart. With more room to move, particles collided less often. Energy slowly thinned out across the growing cosmos. And with that thinning came cooling. The fiery storm of the early universe began to calm. Imagine a crowded room slowly emptying as people leave. The movement becomes less frantic. The noise softens. Space opens between the dancers. That is what expansion did to the universe. After about 380,000 years, the cosmos cooled enough for something remarkable to occur. Electrons and protons, the tiny charged particles that fill the universe, finally slowed enough to combine. They joined together to form the first atoms. Mostly hydrogen. A little helium. And suddenly, the cosmic fog cleared. Photons, the particles of light, were no longer trapped. Instead of constantly colliding with free particles, they could finally travel freely across space. Light was released. Not in a dramatic explosion, but in a gentle moment of cosmic clarity. It was as if a thick mist had lifted, allowing the universe to become transparent for the very first time. The light released during this moment did not disappear. It began traveling through space in every direction, spreading outward as the universe continued expanding. And it has been traveling ever since. For billions of years, those ancient photons have crossed unimaginable distances, moving quietly through the cosmos. But something important happened to them along the way. As the universe expanded, the wavelengths of that light stretched. The energy of the photons slowly decreased. What was once blazing hot radiation gradually cooled, like glowing embers fading after a fire. Over billions of years, that light cooled more and more until it became something incredibly gentle. Microwaves. Today, astronomers call this ancient radiation the cosmic microwave background, often shortened to CMB. It is one of the most remarkable discoveries in modern science. Because this faint glow is not coming from any star or galaxy. It is not produced by planets or nebulae. It is the leftover light from the birth of the universe itself. And it surrounds you everywhere. No matter where you travel in space, the cosmic microwave background is there. It arrives equally from every direction, filling the universe with a soft bath of radiation. Its temperature is extremely low, about 2.7 Kelvin above absolute zero. That is only a few degrees warmer than the coldest temperature nature allows. And yet, even though it is incredibly faint, scientists can measure it with astonishing precision. Sensitive radio telescopes can detect this ancient glow, revealing tiny variations in its temperature across the sky. These variations are incredibly small differences of only a few millionths of a degree. But those tiny differences carry enormous meaning. They are the fingerprints of the early universe. When astronomers map the cosmic microwave background, they are essentially creating a baby picture of the cosmos. A snapshot of the universe when it was only a few 100,000 years old. In these patterns of warmth and coolness, Scientists can see the earliest seeds of galaxies beginning to form. Slightly denser regions of matter would eventually gather more gravity, pulling gas together to create stars and galaxies. From those small variations came everything you see in the universe today. Every galaxy, every star, every planet, even the atoms in your body. All of them trace their origins back to those faint ripples in the ancient glow. As you float quietly through space, the idea begins to settle gently in your mind. The universe is not truly empty. Even the darkest regions of space carry this ancient light. It surrounds you like a soft cosmic memory. And because this background radiation fills every corner of the universe, it creates a kind of temperature floor. No place in ordinary space can easily become colder than this gentle glow. Even the vast emptiness between galaxies is warmed slightly by this leftover energy from the Big Bang. But nature, as it often does, finds subtle ways to surprise us. In rare circumstances, under very unusual conditions, temperatures can drop even lower than this background radiation. Certain clouds of gas can expand so rapidly that they cool beyond the natural temperature of the universe itself. It is a strange and beautiful phenomenon, like finding a pocket of deeper silence within an already quiet world. Somewhere in our galaxy, astronomers have discovered one such place. Its temperature is extremely low, about 2.7 Kelvin above absolute zero. That is only a few degrees warmer than the coldest temperature nature allows. And yet, even though it is incredibly faint, scientists can measure it with astonishing precision. Sensitive radio telescopes can detect this ancient glow, revealing tiny variations in its temperature across the sky. These variations are incredibly small differences of only a few millionths of a degree. But those tiny differences carry enormous meaning. They are the fingerprints of the early universe. When astronomers map the cosmic microwave background, they are essentially creating a baby picture of the cosmos. A snapshot of the universe when it was only a few 100,000 years old. You continue drifting through the vast quiet of the galaxy. The stars are still there, scattered like distant lanterns across the darkness. Each one burns with incredible heat, pouring light and energy into space. Yet between these glowing islands lies something just as important. Space. Not empty space exactly, but a delicate ocean of gas and dust stretching between the stars. Astronomers call this region the interstellar medium, the thin material that fills the galaxy like a faint cosmic mist. At first it may seem almost invisible. The gas is so spread out that even the best vacuum chambers on Earth would feel crowded compared to it. But even something incredibly thin can become enormous when spread across the scale of a galaxy. Over vast distances, this faint mist gathers into giant drifting clouds. These are interstellar nebulae. You begin moving gently toward one of them now. From far away, it appears like a soft shadow drifting through the stars. Its edges are faint, almost dreamlike, stretching across distances so large that light itself takes years to cross them. As you draw closer, the cloud becomes clearer. This nebula is made mostly of hydrogen, the simplest and most common element in the universe. Tiny hydrogen atoms float slowly through the darkness, mixed with traces of helium and small grains of cosmic dust. Each dust grain is smaller than a speck of smoke, yet made of heavier elements like carbon, silicon, and oxygen, materials forged long ago in the hearts of ancient stars. These grains drift quietly through the cloud, like microscopic snowflakes suspended in still air. And here, something remarkable becomes clear. It is cold. Extremely cold. Without nearby stars to warm it, the gas inside many interstellar clouds cools dramatically. Temperatures here may fall to around 10 degrees above absolute zero. That is about minus 263 degrees Celsius. Colder than almost anything naturally found on Earth. In this deep chill, motion becomes slow and gentle. Atoms drift through space at quiet speeds. Collisions between them happen rarely, like distant echoes across a vast silent room. The dancers of the universe are still moving here, but their steps are soft. Their rhythm is calm. And yet, even within this slow and quiet motion, something important is happening. Because cold, in the universe, has a special power. It allows matter to gather. Imagine warm gas for a moment. When atoms move quickly, they bounce apart easily. Their energy pushes them outward, preventing them from settling together. But when gas becomes cold, the story changes. Atoms move more slowly. Their collisions become softer. Gravity, always patiently waiting, begins to take a stronger role. Within these giant clouds, gravity quietly pulls matter together. At first, the change is almost impossible to notice. Slight variations in density appear within the cloud, tiny regions where a few more atoms gather than usual. These denser pockets begin pulling in surrounding gas. Slowly, gently, almost invisibly. Over thousands, even millions of years, these small clumps grow larger. Gravity draws more and more material inward, compressing the gas toward a central region. The cloud begins to form dense cores, small pockets within the nebula where matter is gathering. Inside these cores, temperatures remain incredibly low. Yet pressure slowly increases as more gas falls inward. You may imagine it like a slow cosmic snowfall. Atoms drifting through space eventually settle into the same quiet valley, gathering into deeper and deeper layers. Eventually, something extraordinary will happen. As enough gas collects within one of these dense cores, gravity squeezes the material tighter and tighter. Pressure rises. The core becomes thicker and more compact. And slowly, almost imperceptibly, the temperature begins to rise again. A new star will eventually ignite there. But for now, the cloud remains calm and cold. You drift deeper into the nebula. The darkness here is thicker than the open space between stars. Dust grains floating through the cloud absorb and scatter light, blocking much of the starlight from passing through. These regions are often called dark nebulae because they appear as shadowy shapes against the bright background of the galaxy. Inside them, the universe becomes even quieter. Light fades. Motion slows. Temperatures remain low enough for something delicate and beautiful to occur. Atoms begin forming molecules. In the open spaces between stars, individual atoms usually remain separate because collisions are rare. But inside dense, cold clouds like this one, atoms occasionally meet and gently bond together. Hydrogen atoms join to form hydrogen molecules. Carbon links with oxygen to create simple compounds. Over time, surprisingly complex molecules appear: water, ammonia, methane, and even organic molecules that contain carbon chains. It is quiet chemistry happening across enormous distances. The kind of chemistry that eventually helps build planets, and perhaps even the ingredients for life. All of it unfolding slowly within the cold darkness of interstellar space. You float peacefully through this drifting cloud, surrounded by the faintest motion of atoms and dust grains. The stillness here feels deep and ancient. And yet, within that stillness lies the beginning of countless new stars. The universe, it seems, uses cold not as an ending but as preparation. A moment of quiet gathering before something bright and powerful begins. Eventually, somewhere inside this cloud, gravity will compress gas enough to ignite nuclear fusion. A new star will shine where darkness once drifted. Its light will warm nearby space. Its light will warm nearby space. Its radiation will push against the surrounding gas. And its existence will slowly reshape the cloud that gave birth to it. But for now, the nebula remains patient. Cold. Silent. A place where creation begins in the quietest possible way. As you drift slowly toward the edge of the cloud, the distant glow of stars begins to return. Their light touches frozen worlds scattered throughout the galaxy, planets, moons, and small icy bodies drifting far from the warmth of their parent stars. These worlds experience cold in a different way. Not the delicate cold of drifting gas, but the deep, frozen stillness of solid landscapes locked in cosmic winter. And soon, your journey will carry you toward those distant places. Worlds where sunlight is faint, shadows are endless, and temperatures fall into some of the deepest cold found in our solar system. Out there, beyond the comfortable warmth of the sun, entire landscapes remain frozen for billions of years. And as you begin drifting toward those distant icy worlds, the galaxy slowly reveals another kind of cosmic cold, one written across the surfaces of silent, frozen planets. Your journey carries you gently away from the drifting clouds between the stars and back toward a familiar neighborhood, the quiet outskirts of a solar system. Far away, a star glows softly. It is not as overwhelming from this distance as it once seemed. Its light spreads across vast space, thinning with every passing million kilometers. By the time you arrive in the outer regions of this system, the warmth from that star has faded into something faint and distant. You recognize the star. It is the sun. From Earth, the sun dominates the sky. It pours warmth onto oceans, forests, deserts, and cities. It drives weather, fuels life, and lights each new day. But here, far beyond the inner planets, its power has softened. Sunlight still travels outward, of course. Light moves endlessly across space. But as it spreads, it becomes thinner, weaker, like a lantern seen from a great distance. And in these distant regions, cold begins to take hold. You drift toward a small frozen world. It is not a planet in the traditional sense. Instead, it belongs to a family of distant objects known as dwarf planets and icy bodies. These objects live in the outer edges of the solar system, in regions such as the Kuiper Belt, a vast ring of frozen remnants left over from the formation of the planets. The surface below you is pale and silent. Mountains of ice rise slowly from the landscape. Vast plains stretch across the horizon, covered in frozen nitrogen, methane, and water ice. The sunlight that reaches this surface is dim, no brighter than a gentle twilight. Here, temperatures hover around -220 degrees Celsius. Colder than the coldest winter ever recorded on Earth. Colder than the Antarctic night. And yet, this world is not lifeless in the way you might imagine. The ice beneath your feet is not always solid and unmoving. On some distant worlds, strange forms of frozen activity take place. Icy plains slowly shift over millions of years. Frozen gases form delicate frost across the ground. Some dwarf planets even possess thin atmospheres that appear and disappear as they move along their long, slow orbits around the Sun. Take, for example, the distant world of Pluto. For much of human history, Pluto was simply a tiny point of light in the darkness. Astronomers could see it moving across the sky but knew very little about its true nature. Then, in 2015, a spacecraft named New Horizons finally visited this frozen frontier. What it discovered surprised everyone. Pluto was not just a silent ball of ice. It was a complex world filled with towering ice mountains, vast frozen plains, and mysterious heart-shaped regions made of nitrogen ice. Some of these plains appear smooth and young, suggesting that the ice beneath them slowly churns and flows like thick, frozen lava. Even in the deep cold of the outer solar system, motion still exists. Slow, patient, almost geological in its quiet rhythm. You drift farther outward. Beyond Pluto lies an even more distant region known as the Oort cloud, a vast sphere of icy objects surrounding the solar system. This distant cloud stretches perhaps 50,000 times farther from the Sun than Earth does. Out here, the Sun becomes just another bright star in the sky. Its warmth is almost gone. Temperatures fall toward -270 degrees Celsius, only a few degrees above absolute zero. The icy bodies drifting here spend billions of years in darkness, barely warmed by sunlight. Occasionally, gravity nudges one of them inward toward the Sun, where it becomes a comet, growing a glowing tail as frozen gases vaporize in the increasing heat. But most of these objects remain here, silent and untouched, orbiting the Sun in enormous slow arcs that take millions of years to complete. You imagine standing on one of these distant icy fragments. The sky would be breathtakingly clear. Stars would shine fiercely against the darkness. Without an atmosphere to scatter light, the universe would appear sharp and brilliant. Yet the Sun itself would look small. Just a bright point among thousands. Its warmth would barely touch you. Here, the cold feels deeper than simple temperature. It feels like time has slowed. Without weather, without flowing water, without warm winds or changing seasons, the landscape changes only over immense stretches of time. 1 billion years might pass with only subtle shifts in the frozen surface. Cracks slowly widen. Ice shifts beneath gravity. Dust from distant collisions settles gently across the ground. The universe moves slowly in these places. And that slowness carries a strange kind of beauty. Because even here, in the frozen outskirts of a solar system, the story of the cosmos continues. The atoms inside the ice still vibrate faintly. The faint warmth of the cosmic microwave background still reaches these distant worlds. Gravity still shapes their slow orbits. Nothing in the universe is truly motionless. Cold simply slows the rhythm of change. As you drift away from these frozen bodies, leaving the quiet outer solar system behind, your journey begins moving once again toward the dark clouds of the galaxy. Because even colder places exist beyond these icy worlds. In the deep interiors of certain nebulae, vast clouds hidden from starlight, temperatures fall even lower than those on distant planets. Inside those clouds, atoms move so slowly that something delicate begins to happen. Simple molecules form. Tiny fragments of cosmic chemistry quietly assemble within the darkness. These regions are known as giant molecular clouds, and they are among the coldest environments in the galaxy. They are silent, shadowed places where matter gathers and prepares for the birth of new stars. And as you drift gently toward those enormous dark clouds, you begin to realize that the coldest regions of the universe are often the most creative. Because within their frozen stillness, the ingredients of future worlds are slowly coming together. You continue your quiet journey through the galaxy, drifting gently away from the frozen outskirts of distant planetary systems. Behind you lie the icy worlds of the solar system's far frontier, silent landscapes shaped by faint sunlight and deep cosmic cold. Ahead of you now waits something even more mysterious. A region where darkness gathers more deeply. A place where enormous clouds drift across the galaxy like slow-moving shadows. From a distance, these clouds appear almost invisible, faint shapes against the glow of distant stars. But as you move closer, their true scale begins to reveal itself. They are enormous. Some stretch across hundreds of light years, containing enough material to form thousands of stars. Yet despite their vast size, they remain fragile and diffuse, like a cosmic fog drifting through space. Astronomers call these immense regions giant molecular clouds. And they are among the coldest places in the entire galaxy. You glide slowly toward the edge of one of these clouds now. At first, the change is subtle. Starlight begins to dim as tiny grains of dust scatter and absorb the light passing through the cloud. The sky around you grows darker, softer, more muted. Dust particles drift everywhere here. Each one is incredibly small, often less than a micron across. Yet these microscopic grains play an important role in shaping the universe. They act like tiny shields, blocking harsh radiation from nearby stars. Without that radiation, the gas inside the cloud can cool even further. And cool it does. Temperatures here drop to about 10 degrees above absolute zero, sometimes even lower in the densest regions. That is roughly minus 263 degrees Celsius. In such deep cold, the movement of atoms becomes incredibly slow. Imagine again the dancers of the universe, the atoms and molecules that make up everything around you. In warmer environments they move energetically, colliding often and bouncing apart. But here, in the cold heart of a molecular cloud, their movements are gentle and unhurried. Collisions between atoms are rare and delicate. And when atoms do meet, something special can occur. They can begin to bond. Inside these clouds, hydrogen atoms often meet upon the surface of dust grains. When two hydrogen atoms settle on the same grain, they may combine, forming a hydrogen molecule. This simple molecule, two hydrogen atoms joined together, is the most common molecule in the universe. From these humble beginnings, more complex chemistry can slowly unfold. Carbon atoms drift through the cloud. Oxygen atoms follow. When conditions are calm enough, these elements begin forming simple molecules: carbon monoxide, water vapor, ammonia, methane. Tiny combinations of atoms quietly assembling in the cold darkness. It is a form of cosmic chemistry that happens incredibly slowly, sometimes taking thousands or millions of years for molecules to build up within the cloud. But time, in the universe, is rarely in short supply. the galaxy is patient. And within that patience, molecules gather. As you drift deeper into the cloud, the darkness thickens. Some regions of molecular clouds are so dense with dust that almost no visible light can escape. Astronomers call these regions dark nebulae. From Earth, they appear as mysterious black shapes blotting out the background stars. But inside these dark regions, something extraordinary is happening. Matter is quietly gathering. Gravity, gentle but persistent, pulls gas and dust towards slightly denser pockets within the cloud. Over time, these pockets grow heavier, pulling in even more material. These dense pockets are called molecular cores. They are the coldest regions of the cloud, often reaching temperatures only a few degrees above absolute zero. Here, atoms drift so slowly that the entire environment feels almost suspended in time. But gravity continues its work. Slowly, the cores become denser. Gas falls inward. Pressure begins to rise. The process is incredibly gradual. Thousands of years pass with only subtle changes. Then tens of thousands. Then hundreds of thousands. Yet eventually, the growing pressure inside these cores reaches a turning point. The material begins collapsing inward more rapidly under its own gravity. A newborn star is beginning to form. But before that brilliant moment arrives, the cloud remains in its quiet phase, a long period of preparation when cold allows matter to gather undisturbed. In these deep shadows, some of the most complex molecules ever discovered in space have been found. Astronomers using radio telescopes have detected molecules containing dozens of atoms, including organic compounds that resemble the chemical building blocks of life. Sugars, alcohols, even amino acid precursors. These molecules are not life themselves, but they demonstrate something remarkable. The chemistry of life begins long before planets even exist. It begins here, in the cold darkness of interstellar clouds. You drift slowly through one of these regions now, surrounded by faint whispers of chemistry unfolding across light years of space. Every molecule here is part of a larger story. Eventually, when new stars ignite within the cloud, the surrounding material may form protoplanetary disks, swirling rings of gas and dust that give birth to planets. Those planets may inherit the molecules formed in this cold cloud long before their star was born. In this way, the cold hearts of molecular clouds quietly prepare the ingredients for future worlds. The story of planets, oceans, atmospheres, and perhaps even life often begins in these dark regions. And yet, despite all this slow activity, the cloud itself remains profoundly calm. You float through a region where the only sounds would be the softest imaginable collisions between drifting particles. No wind. No roaring storms. Only gentle motion across unimaginable distances. Cold has slowed everything here. But it has not stopped the universe from creating. Eventually, as more stars ignite within the cloud, powerful radiation and stellar winds will begin shaping the surrounding gas. Some regions of the nebula will glow brightly, illuminated by newborn stars. Other regions will be blown apart, scattering their material across the galaxy. But in this moment, the cloud remains quiet and undisturbed. A cradle of slow cosmic preparation. As you drift toward the outer edges of the nebula, the darkness gradually begins to thin. Starlight filters back into view, faint at first, then brighter as you leave the densest dust behind. The galaxy opens once again around you. But somewhere out there, far beyond this particular cloud, exists a place that pushes the limits of cosmic cold even further. A strange nebula where expanding gas cools to temperatures lower than the background temperature of the universe itself. A place where the dance of atoms slows almost beyond imagination. Astronomers call it the Boomerang Nebula. And as your journey carries you quietly through the galaxy, you begin drifting toward that extraordinary region, toward the coldest natural place ever discovered in the universe. Your journey through the galaxy continues, drifting beyond the quiet molecular clouds where stars are slowly preparing to be born. Those regions were already astonishingly cold. Yet the universe, with its endless variety, holds places even more extreme. Somewhere among the stars lies a nebula unlike any other, a strange cloud where the temperature drops below the faint warmth that fills the universe itself. You begin to approach it now. At first, it appears like a soft and distant blur among the stars. Its shape is faint and delicate, almost like the outline of wings spreading through space. Astronomers gave it a curious name when they first observed it through powerful telescopes. They called it the Boomerang Nebula. The name comes from its shape. When viewed in certain wavelengths of light, the cloud appears to curve outward like a pair of sweeping arcs, resembling the shape of a boomerang gliding through the air. But its appearance is not what makes this nebula truly extraordinary. What makes it remarkable is its temperature. To understand why, you recall something from earlier in your journey. Everywhere in the universe, a faint background glow exists, the ancient radiation left over from the Big Bang. This glow gently warms all of space to about 2.7 Kelvin above absolute zero. That means most regions of space cannot easily become colder than this background temperature. It acts like a quiet cosmic blanket. Yet the Boomerang Nebula somehow manages to slip beneath that blanket. As you drift closer, the reason slowly becomes clear. The nebula is not a calm, motionless cloud. Instead, it is expanding rapidly outward from a dying star located at its center. Long ago, that star began shedding its outer layers, sending enormous streams of gas rushing into space. This gas continues to expand even now. And when gas expands quickly, something remarkable happens. It cools. You may have experienced a tiny version of this effect before. When air escapes quickly from a spray can or compressed container, the container often feels cold to the touch. As the gas expands, its molecules spread out and lose energy. The same physical principle operates here, but on an enormous cosmic scale. Gas is racing outward from the dying star at incredible speed, spreading rapidly across space. As it expands, its temperature falls dramatically. The result is astonishing. Measurements from radio telescopes show that parts of the Boomerang Nebula have cooled to about 1 Kelvin above absolute zero. That is colder than the cosmic microwave background itself. In other words, this nebula contains a region colder than the natural background temperature of the universe. It is, in a sense, a pocket of deeper stillness within the cosmic ocean. You drift quietly along the outer edges of this remarkable cloud. The gas here is extremely thin, almost unimaginably sparse. But its temperature is so low that the motion of atoms becomes incredibly slow. The dancers of the universe move here with the smallest possible steps. The nebula itself stretches across a region about 2 light-years wide. For comparison, that is roughly half the distance between our Sun and the nearest star system. Yet even across this enormous span, the expanding gas continues to cool as it spreads outward. At the heart of the nebula sits the star that created it. Once, this star was similar to our Sun, a steady fusion reactor shining gently for billions of years. But as stars age, their internal balance begins to change. Eventually, many stars enter a stage where their outer layers become unstable. They swell, grow brighter, and begin shedding gas into space. Over time, these layers drift away entirely, forming a glowing shell around the dying star. Astronomers call these beautiful structures planetary nebulae, though the name is somewhat misleading. They have nothing to do with planets. Early telescopes simply made them appear vaguely planet-shaped. The Boomerang Nebula is related to this process, though it represents a slightly earlier stage. Here, the dying star has expelled enormous quantities of gas, forming a thick envelope around itself. Powerful outflows from the star continue pushing this gas outward at tremendous speed. It is this rapid expansion that creates the extraordinary cold. You float quietly through the nebula, imagining what it would feel like if you could experience such an environment directly. The cold here would be unlike any earthly winter. Not the biting chill of wind or snow. Instead, it would feel like the slowing of motion itself. Atoms drifting gently. Energy fading into stillness. The entire environment feels suspended between movement and rest. And yet, even in this extreme cold, the laws of physics remain quietly at work. Atoms continue vibrating ever so slightly. Radiation still flows through space. Gravity continues guiding the motion of stars and gas. The universe never fully stops. It only slows. As astronomers studied the Boomerang Nebula, they realized something deeply fascinating. This extraordinary cold is temporary. The expanding gas will not remain this cold forever. Eventually, the surrounding radiation from nearby stars, and even the faint cosmic microwave background, will slowly warm the nebula again. Over thousands of years, its temperature will gradually rise. The pocket of extreme cold will fade. Like frost melting under distant sunlight. This reminds you of something beautiful about the universe. Even its most extreme conditions are often temporary moments within longer cosmic stories. The Boomerang Nebula represents one brief chapter in the life of a star, a fleeting stage where expanding gas cools beyond the natural temperature of space itself. A quiet record of change unfolding across thousands of years. You drift slowly past the outer edges of the nebula now. Behind you, the strange cloud fades back into the wider galaxy. Ahead of you, the stars glow once again across the darkness. And your journey begins to turn gently back toward a very different place. Because while the Boomerang Nebula shows how nature can create extraordinary cold in space, scientists on Earth have learned how to approach similar temperatures within carefully designed laboratories. Using delicate experiments, lasers, and magnetic fields, researchers have cooled atoms to temperatures only billionths of a degree above absolute zero. In those quiet laboratories, matter begins to behave in ways almost as strange as the coldest nebulae. And as your journey slowly returns toward the small blue planet where those experiments take place, you begin to explore how humans have learned to create some of the coldest environments ever produced. Places where the dance of atoms slows almost to stillness. Your journey now turns gently back toward a familiar place. After drifting across nebulae, frozen worlds, and the coldest natural clouds in the galaxy, you begin returning to a small blue planet orbiting a quiet yellow star. Earth. From space, it glows softly, swirls of white clouds drifting across deep blue oceans, continents resting beneath sunlight. Compared with the frigid depths of the galaxy, Earth feels warm, lively, and full of motion. Wind moves through forests. Waves roll across oceans. Cities glow with restless human activity. Yet hidden inside certain quiet buildings on this planet are rooms where scientists attempt something extraordinary. They try to create the coldest temperatures ever produced. Inside these laboratories, researchers explore the very limits of temperature itself, approaching the boundary known as absolute zero, the place where atomic motion becomes almost perfectly still. You drift gently inside one of these laboratories now. The room is calm and carefully controlled. Machines hum softly. Instruments glow with tiny lights. Everything here is designed to measure delicate changes in energy and motion. At the center of the room sits a small experimental chamber. Inside that chamber, scientists are preparing atoms for an unusual journey. To understand what they are doing, you return once again to the tiny dancers of the universe. Atoms move constantly. Even in extremely cold environments, they still vibrate and drift through space. Their motion represents energy, and temperature is simply a measure of how energetic those motions are. To cool atoms, scientists must remove that energy. But how can you slow something as small as an atom? The answer involves light itself. One of the most elegant techniques used in modern physics is called laser cooling. At first, this idea may sound surprising. Lasers are usually associated with heat and power. They cut metal, burn materials, and deliver intense energy. Yet under the right conditions, lasers can also remove energy from atoms. Imagine an atom drifting slowly through space. If a carefully tuned laser beam shines toward it, the atom can absorb a photon of light from that beam. When it absorbs the photon, the atom receives a tiny push in the direction of the light. Scientists arrange several lasers pointing toward the atom from different directions. As the atom moves, it tends to absorb photons that oppose its motion, gently pushing it back. Each interaction slows the atom slightly. The effect is delicate but powerful. Over time, thousands of these tiny pushes gradually reduce the atom's motion. The dancers slow. Their steps become smaller. Their rhythm softens. Within these laser fields, atoms can be cooled to temperatures only millionths of a degree above absolute zero. But scientists do not stop there. Once atoms have been slowed with lasers, they often place them inside magnetic traps, invisible fields that hold the atoms in place. Inside these traps, further cooling techniques can remove even more energy. One such method is called evaporative cooling. The idea is similar to how a hot drink cools as steam rises from its surface. The most energetic molecules escape first, carrying away heat. In the atomic trap, the fastest-moving atoms are allowed to escape, leaving behind the slowest ones. As those energetic atoms disappear, the remaining atoms become colder and colder. Eventually, scientists can cool these atomic clouds to temperatures only billionths of a degree above absolute zero. These temperatures are far colder than anything naturally found on Earth. Even colder than the coldest regions of space. Inside these experiments, something fascinating begins to happen. When atoms become this cold, their behavior changes dramatically. Normally, atoms act like individual particles, tiny objects moving independently through space. But at extremely low temperatures, the rules of quantum mechanics begin to dominate their behavior. Particles start acting less like separate objects and more like waves. Their identities blur together. Instead of moving independently, large groups of atoms begin sharing the same quantum state. In other words, they begin behaving almost like a single giant atom. This strange form of matter is known as a Bose-Einstein condensate, named after the physicists who first predicted its existence many decades ago. Within a Bose-Einstein condensate, atoms move together in perfect harmony. Their motions synchronize like dancers following the same slow rhythm. Scientists often describe it as matter behaving like a single coherent wave. In this state, quantum effects that are usually hidden in everyday life become visible on a human scale. The behavior of the condensate can reveal deep truths about the nature of matter, energy, and the underlying structure of reality. Experiments with these ultra-cold systems have helped scientists explore topics ranging from superconductivity to the fundamental nature of quantum mechanics itself. And all of it becomes visible only when motion slows enough. Cold reveals hidden layers of the universe. It allows researchers to study the quietest behaviors of matter, behaviors that are normally drowned out by the energetic motion of warmer environments. As you drift quietly through the laboratory, the idea settles gently into your thoughts. The coldest places in the universe are not only distant nebulae or frozen planetary systems. Sometimes they exist inside carefully controlled chambers on a small planet orbiting an ordinary star. In those silent rooms, human curiosity reaches toward the deepest limits of nature, approaching but never quite touching absolute zero. And as atoms inside those chambers grow colder and colder, they begin revealing a mysterious world where matter behaves in ways that feel almost magical. A world where particles merge into waves, and motion becomes a shared rhythm. In the next stage of your journey, you will step more deeply into that strange quantum stillness. Because when matter approaches the quiet boundary of absolute zero, the universe begins to show some of its most surprising secrets. You remain in the quiet laboratory for a moment longer. The room is calm. Instruments glow softly, and the faint hum of machines creates a gentle rhythm in the background. Inside the experimental chamber, a small cloud of atoms floats in a delicate balance of magnetic fields and laser light. To the eye, it might appear like almost nothing at all. A faint, mist-like blur. Yet inside that tiny cloud, something extraordinary is unfolding. The atoms within have been cooled to temperatures unimaginably close to absolute zero. Their motion has slowed so dramatically that they are now moving thousands of times more slowly than atoms in ordinary air. The dancers of the universe have nearly come to rest. And when motion becomes this slow, the hidden rules of nature begin to appear. You remember how, in everyday life, objects behave in familiar ways. A ball rolls across the ground. A drop of water falls downward. Particles move like tiny separate objects. But in the strange and subtle world of quantum mechanics, particles are not always simple objects. Sometimes they behave like waves. In fact, every particle in the universe carries both identities at once. It can act like a tiny point of matter, and also like a wave spreading gently through space. Normally, this wave-like nature is impossible to see. The warmth and motion of everyday environments blur the delicate patterns created by these waves. Atoms move too quickly. Their wave patterns overlap chaotically and disappear into noise. But when atoms become extremely cold, something remarkable happens. Their movements slow enough for their wave nature to grow larger. The waves begin to spread. You may imagine it like ripples on the surface of a calm lake. When only a single pebble touches the water, the ripples spread outward in smooth circles. But when many pebbles fall at once, the ripples overlap in complex patterns. At ordinary temperatures, atoms behave like countless pebbles striking the lake at random. Their wave patterns collide and interfere in complicated ways. Yet when atoms are cooled almost to absolute zero, their waves begin to expand so widely that they overlap gently with one another. Instead of many separate ripples, something new appears. The waves merge. The atoms begin sharing the same wave pattern. At this moment, a new state of matter emerges. It is called a Bose-Einstein condensate. Inside this unusual state, thousands or even millions of atoms behave as if they are part of a single unified quantum wave. Instead of moving as individuals, they move together. Their motions become synchronized, like dancers following the same slow, graceful choreography. This phenomenon was first predicted nearly a century ago by two brilliant physicists, Satyendra Nath Bose and Albert Einstein. They realized that under extremely cold conditions, certain types of particles could collapse into the same quantum state. For decades, this idea remained purely theoretical. The temperatures required were far beyond what technology could achieve. But in 1995, scientists finally succeeded. Using advanced laser cooling and magnetic trapping techniques, researchers created the first Bose-Einstein condensate in a laboratory. When they observed the cloud of atoms, something astonishing appeared. Instead of behaving like separate particles, the atoms formed a single coherent wave, one that could be measured and observed directly. It was like watching quantum mechanics step out of the microscopic world and into the visible realm. You drift closer to the chamber in the laboratory. Inside, the atoms float almost motionless, held gently within their invisible magnetic cage. Their shared wave spreads through the cloud like a soft glow of probability. In this strange state, matter behaves differently from anything you experience in everyday life. For example, when scientists allow a Bose-Einstein condensate to flow through narrow channels, it can move without friction. This property is related to a phenomenon called superfluidity, where liquids flow endlessly without losing energy. Imagine a fluid that can climb the walls of a container, or circle endlessly through a loop without slowing down. These behaviors sound almost magical. Yet they arise naturally when matter becomes cold enough for quantum mechanics to dominate. In this deep quiet of near absolute zero, the universe begins revealing its most subtle patterns. You begin to notice something beautiful about this idea. Cold does not simply remove energy. It reveals structure. When motion slows, hidden layers of reality become visible. Just as calm water allows you to see reflections clearly, the stillness of extreme cold allows scientists to observe the delicate wave nature of matter itself. And these discoveries are not merely curiosities. Understanding quantum behavior has led to technologies that shape modern life. Lasers, magnetic resonance imaging, quantum sensors capable of measuring gravity and motion with astonishing precision. Some scientists even believe that studying these ultra-cold systems may one day help create quantum computers, machines capable of solving certain problems far beyond the reach of ordinary computers. All of this knowledge grows from a simple idea: slow the atoms enough, and the deeper rules of nature become visible. You pause for a moment, letting that thought settle. Across the universe, cold environments, from nebulae to distant planets, slow the motion of matter. Here on Earth, human curiosity has learned how to create similar stillness within tiny experimental chambers. And in that stillness, matter begins revealing the wave-like nature hidden inside everything. It is a reminder that the universe contains layers of reality we rarely see. Warm environments are full of activity and noise. But in the quietest places, where motion slows almost to nothing, the deeper harmony of nature appears. You slowly drift away from the laboratory now, rising once again above the surface of the Earth. The blue planet turns gently beneath you. Beyond it lies the vast darkness of space. And somewhere out there, the universe itself continues its slow and steady cooling. Stars will not burn forever. Galaxies will not shine eternally. Over unimaginable stretches of time, the cosmos itself is drifting toward a colder future. A future where motion slows across trillions of years. And as you look out into that distant future, you begin to wonder what the universe might become when its warmth finally fades into near-perfect stillness. You leave the laboratory behind, rising gently above Earth, and drift once again into the vastness of space. The stars around you sparkle as familiar companions, but your gaze extends far beyond the galaxies you know, into a future so distant it seems almost like a dream. In this quiet future, time itself flows slowly, stretching across trillions of years. Stars that today blaze with energy will have exhausted their fuel. Massive suns will collapse into dense remnants, white dwarfs, neutron stars, or black holes, while smaller stars fade quietly into darkness. The bright tapestry of the cosmos gradually dims, leaving galaxies faint and sparse. The warmth of starlight, which has shaped the rhythms of planets and life, begins to fade from the universe. In its place, a deep chill spreads. Temperature, the measure of motion in matter, slowly approaches a profound stillness. The atoms in distant clouds, in dying stars, and in cold planetary remnants move ever more gently, vibrating with less and less energy. Yet the universe is never truly silent. Even as motion slows, tiny whispers of energy persist. Cosmic radiation drifts across the void, a faint echo of the Big Bang that began it all. Even in regions where stars have long since burned out, photons and neutrinos wander endlessly, carrying fragments of past activity through space. The quietest places remain filled with subtle motion, a reminder that the cosmos never stops completely. As you drift among the fading galaxies, you notice how cold transforms the universe into a contemplative place. Temperature here is not just the absence of heat, it is the slow rhythm of change. Planets, stars, and dust clouds all participate in a gentle, cosmic ballet, their motions quieted over unimaginable spans of time. It is as if the universe itself is taking a deep, timeless breath. Some remnants of matter, such as white dwarfs, continue to shine faintly, glowing softly in the dim light of the dying cosmos. These stars, once bright and energetic, now radiate only a fraction of their former warmth. Their cooling is gradual, stretching over billions of years, and eventually even they will fade into cold, dark cinders drifting through space. The galaxies themselves, once bustling with the formation of new stars, grow quieter. Interactions between galaxies, collisions, mergers, and bursts of star formation become increasingly rare. Gravity continues its patient work, but the material it manipulates moves more slowly, its motion softened by time. The universe's energy becomes diffused across greater and greater distances, leaving a pervasive calm in its wake. Yet even in this distant future, cold is not lifeless. Subatomic particles continue their subtle dances. Quantum fluctuations still ripple through the vacuum, tiny tremors in the fabric of space-time. Black holes, slowly evaporating via Hawking radiation, release faint quanta of energy that drift across the universe. In these quiet corners, matter and energy interact in ways both subtle and profound, hinting at layers of reality beyond our present understanding. You glide past a cluster of ancient stars, their remnants orbiting each other in slow, quiet arcs. Comets and icy bodies drift silently through interstellar space, having long been liberated from the influence of active stellar systems. Even in this immense stillness, gravity ensures that structure persists. The universe retains a delicate balance, a faint framework against which the slow dance of energy continues. Time, on these scales, seems almost meaningless to the mind accustomed to days and years. Billions of years pass between meaningful events. Stars blink out, galaxies fade, and energy dissipates. Yet in the vast stillness, there is a profound beauty, a quiet majesty in the slow, methodical cooling of everything. The universe appears to be resting, not in emptiness, but in a deep, contemplative calm. As you move further, the cosmic microwave background radiation, once the lingering warmth from the Big Bang, has redshifted to near invisibility. Space itself stretches, expanding silently, carrying galaxies away from one another. The energy density drops, leaving a colder, quieter cosmos. Temperature continues to approach near absolute zero in vast stretches of the void. Motion becomes ever more subdued. But even as the universe grows colder and emptier, subtle hints of life's building blocks may persist in isolated pockets. Molecules and dust, remnants of long-extinct stars and planets, drift slowly through the void. Perhaps somewhere, long after stars have gone out, chemical processes could occur, tiny acts of creation in the most unexpected places. Cold does not prevent wonder, it merely transforms it into something patient, gentle, and enduring. You glide past ancient black holes, the densest relics of stars long extinguished. They exert gravity across immense distances, shaping the sparse remnants of galaxies with invisible hands. Slowly, even these titanic objects lose energy through Hawking radiation, a faint whisper of quantum mechanics in the deep stillness of space. Though these processes are imperceptibly slow, they remind you that change never ceases completely. And yet, in all this cold, a pattern emerges. Cold is not the enemy of motion or creation, it is a shaping force. Just as frozen molecular clouds once allowed stars to form, the gradual cooling of the universe imposes a slow rhythm upon matter and energy, stretching cosmic processes across unimaginable durations. In the stillness, the underlying patterns of physics become apparent, visible not in sudden bursts, but in patience and persistence. As you drift even further into the distant future, you notice the faint glow of surviving white dwarfs, the slow arcs of lingering planets, and the quiet hum of radiation from fading galaxies. Temperature is approaching near perfect stillness, but the universe continues its patient dance. Energy, matter, and gravity interact subtly, quietly maintaining a cosmic story that will unfold over trillions of years. You pause and take in the vast, silent beauty of it all. The universe, once roaring with energy and light, has become a place of gentle, measured stillness. Cold dominates, but it does not diminish wonder. Instead, it frames it, allowing you to see the enduring elegance of cosmic processes, slow, deliberate, and timeless. And as you continue to drift through this quiet universe, your thoughts begin to turn back toward the present. From the distant Boomerang Nebula to laboratory chambers on Earth, from icy planetary worlds to molecular clouds, the story of cold has unfolded in many forms. Each environment, from the faintest whispers of energy to the slowest dancing atoms, reflects the same principle. When motion slows, the universe begins to reveal layers of subtle beauty. Somewhere ahead lies the return to the comforting warmth of the present moment, where the cosmos feels close enough to touch, even as its infinite expanse stretches beyond comprehension. But for now, you float in the deep calm of the cooling universe, where every particle moves slowly, every atom vibrates softly, and the rhythm of existence itself whispers in almost imperceptible tones. And as the distant galaxies fade into shadows of light, you realize that even in the coldest, quietest reaches of space, life, motion, and energy leave traces, tiny reminders that the universe, while slowing, is never truly still. Somewhere, in the soft hush of cosmic time, the dance continues. You begin your gentle descent from the distant future of the universe, leaving behind the faint, fading glow of long-extinguished stars and slowly cooling galaxies. The vast stretches of space that once seemed impossibly remote now feel closer, carrying a comforting rhythm in their silence. The cosmos, which has unfolded across billions and trillions of years, now feels like a quiet companion, not an empty void. The cold that once seemed harsh or alien now settles around you like a soft blanket. In every direction, the universe stretches infinitely, yet it carries a sense of calm. The atoms in the space around you move slowly, almost imperceptibly, their vibrations gentle, rhythmic, and soothing. Motion, though diminished, continues in a serene, harmonious way. You think back to the Boomerang Nebula, the molecular clouds, and the frozen planetary worlds you have visited. Each place, while extraordinarily cold, held a unique beauty. The stillness revealed layers of existence that warmth alone might obscure, the faint dance of atoms, the delicate emergence of molecules, the preparation of matter for future creation. Cold is not simply the absence of heat, it is a lens through which the universe's hidden poetry becomes visible. Here on Earth, you recall the laboratories where atoms were cooled to near absolute zero. In those carefully controlled chambers, matter behaved in ways that felt magical. Particles merged into waves, dancing together in perfect synchronization. The cold revealed quantum patterns that are invisible in everyday warmth and chaos. There, as in the far reaches of space, stillness became a path to understanding, a quiet bridge connecting physics and wonder. As your awareness shifts, you notice that even your own body carries its own sense of temperature. The warmth of your skin, the rhythm of your heartbeat, and the flow of blood are all gentle movements of energy within you. And when you pause, breathe deeply, and settle into stillness, you feel a resonance with the slow, measured rhythms of the cosmos. You sense that the same principles of motion, energy, and quiet order that govern the distant universe are present within you as well. You allow yourself to drift into this awareness, feeling a calm connection with the vastness around you. time itself seems to stretch and soften. The events of the distant past, the intricate processes of quantum behavior, and the slow cooling of galaxies all blend into a gentle rhythm that your mind can follow without strain. Every atom, every photon, every distant star participates in this universal dance, and yet it feels patient, gentle, and unhurried. In this state, the concept of cold transforms. It is no longer a harsh emptiness but a profound comfort. Cold slows motion without halting it, revealing patterns that warmth might obscure. It teaches patience, reflection, and presence. You feel as though the universe itself is exhaling, allowing everything to settle into a soft, meditative pause. Your gaze drifts outward once more, beyond the familiar constellations, past the distant galaxies and nebulae, and into the silent void that stretches between them. The space is filled with faint traces of motion, the soft hum of radiation, the drift of particles, and the subtle pull of gravity acting across unimaginable distances. Even here, in what seems like emptiness, there is life and motion, slow but deliberate. The vastness of space, once overwhelming, now feels welcoming. You understand that stillness and cold are not signs of emptiness or abandonment, they are the universe's way of creating space for reflection, growth, and continuity. In the calm, you feel the presence of processes that are invisible to the hurried mind, subtle patterns that unfold over timeframes far beyond human comprehension. And yet, even in this deep cosmic calm, there is hope. Cold does not prevent creation, it merely delays it. The atoms in interstellar clouds will one day come together to form new stars. Molecules hidden in distant nebulae may drift into emerging planets, laying the foundation for future possibilities. Even in the quietest corners, the universe preserves the potential for change, growth, and wonder. You find yourself settling deeper into this awareness. The sensation of cold, once alien or intimidating, has become a companion, a teacher guiding you toward patience, reflection, and serenity. Motion, energy, and matter, though slowed, continue to hum softly around you, and the rhythm of the universe becomes a lullaby of subtle vibrations, gentle waves that carry you toward calm. Your thoughts drift like the faint glow of distant stars, each one a reminder that even vast emptiness can be comforting. The universe, in its grand, slow unfolding, mirrors the quiet spaces within your own mind. Every atom in the cosmos vibrates with purpose, every quantum fluctuation carries meaning, and every star, whether blazing or fading, contributes to the infinite tapestry of existence. You imagine resting in that cosmic stillness, cradled by the gentle presence of the universe itself. Temperature, energy, motion, these are no longer abstract concepts but elements of a quiet harmony you can feel and follow. Cold is not something to fear, it is a state of balance, a lull that allows reflection and understanding to emerge. The distant lights of fading galaxies cast soft shadows across the cosmic stage, illuminating the vast interplay of matter and energy in a muted, tranquil glow. You float among them, feeling neither small nor insignificant, but part of the larger, calming rhythm that connects everything across space and time. And as you continue to drift, guided by the gentle hum of motion and the quiet presence of cold, you realize that the universe, vast, ancient, and still, is a place of comfort as well as wonder. Its stillness is not emptiness but a sanctuary, a reminder that in slowing down, patterns emerge, connections appear, and the dance of existence can be appreciated in all its gentle complexity. Here, in this serene space, you begin to understand that cold and stillness are gifts. They create room for thought, for wonder, for reflection. They reveal the deep order of the cosmos and allow you to witness the quiet choreography of existence. And as you rest within this awareness, you feel a profound sense of peace, a comfort that stretches from the tiniest particles of matter to the farthest reaches of the galaxy. Somewhere beyond the distant stars, in the slow drift of cold and stillness, the universe continues its gentle, patient rhythm. And as you settle into that rhythm yourself, you carry the quiet comfort of cosmic stillness with you, a gentle companion in the present moment, reminding you that even in the vast cold, there is warmth in understanding, serenity in awareness, and calm in being.